After the Second World War, because of the obvious importance of physics research, many laboratories all over the world began to build accelerators for studying the structure of nuclei. In particular, in the United States, there were accelerators built first in Brookhaven National Laboratories on the East Coast, then at the Lawrence Radiation Laboratory at Berkeley on the West Coast. So in the 1950s, with several new accelerators, many new particles were found, and that was the beginning of what was called high-energy physics or elementary particle physics. The quantum numbers, charge, spin, parity, and quantum numbers due to other symmetries of these particles were the main subject of study in the 1950s. And in particular, there were particles found which were called theta, and they decay into 2 pi mesons. And tau was another particle which decayed into 3 mesons. These decays were first found in cosmic rays. Later on, when accelerators were built, they were also produced in the laboratory and could be studied much more easily. And there was a puzzle. The puzzle was called the theta-tau puzzle. The meaning of the puzzle is as following. It was found that pi has a quantum number called parity, which is related to right-left symmetry. Pi has a parity of -1. That was determined earlier in the early 1950s. The theta has decays to 2 pi's, and so therefore it has a parity of -1 to the second power, namely +1. Tau decays into 3 pi's, so therefore it has a parity of -1 cubed, and therefore it is a parity of -1. So theta and tau do not have the same parity. But on the other hand, the other experiments show that theta and tau have experimentally equal lifetimes and equal masses. So the main question around 1955-56 was theta and tau the same particle? There are strong arguments for saying that they are the same particle as seen on this slide. But there are equally strong arguments saying that they cannot be because they have different parities. So that was called the theta-tau puzzle. So this was perhaps the dominant question in particle physics in the years 1955 and 1956. T.D. Lee and I looked into this, as in fact most of the elementary particle theorists were working on this. So we finally asked, what was the basis of belief in parity conservation? The answer was there were many beta decay experiments. Beta decay had been studied since actually the beginning of the 20th century. By the 1930s and 1940s, hundreds and even thousands of experiments on beta decay had been performed. And so beta decay was understood quite well. In particular, the selection rules and the intensity rules for beta decay had been calculated and was in excellent agreement with experiment. And among these selection rules, there is the parity selection rule. And those parity selection rules were in agreement with experiment in hundreds of experiments. So therefore, that was in some sense the most accurate belief in the conservation of parity for nuclear physics. When Lee and I examined this question, after a lot of calculation, we finally found that in 1956 that was not the case. People had mistakenly believed that the parity conservation had been proven by the beta decay experiments. Later on, after parity conservation was shown to be not valid, I had written the following passage. Previous experiments, though they confirmed parity selection rules, had in fact not proved right-left symmetry. The fact that parity conservation in the weak interactions was believed for so long without experimental support was very startling. But what was more startling was the prospect that a space-time symmetry law, which the physicists have learned so well, may be violated. This prospect did not appeal to us. Rather, we were, so to speak, driven to it through frustrations with the various other efforts at understanding the theta-tau puzzle that had been made. What we are saying here, what I said here, after parity conservation was experimentally found to be not valid, was that first, we didn't like to have parity non-conservation. And in fact, that was what everybody had an obsession on. But when we examined in detail, we find that previous belief that parity was conserved in nuclear decays was in fact not founded. Why was it not founded? It was because up to then, all the beta decay experiments, hundreds of beta decay experiments, did not measure a quantity which is a pseudoscalar. What is a pseudoscalar? These two are examples of pseudoscalars. P1 dot P2 cross P3 and P dot sigma. If you want to P1 dot P2 cross P3, if you do this in a mirror, then it becomes a minus P1 dot minus P2 cross minus P3. It changes sign. That is a quantity which is different for the mirror image from the original. Also, P dot sigma. Sigma is the spin. The sigma reflected in a mirror does not change sign. So P dot sigma reflected in the mirror changes sign. If you do an experiment with these quantities measured, then you can tell whether parity is conserved or not. But we showed that all previous experiments in beta decay did not have such a complexity. So we proposed that one should do this test, namely do an experiment for which either P dot P cross P or P dot sigma changes sign, and then you can tell whether parity is conserved. And this is the principle of the experiment. If you have a cobalt nucleus, cobalt was known to decay by beta decay, and if you have a counter underneath it, so you have a cobalt nucleus beta decaying, and this beta decay intensity is counted in the counter here. The mirror image experiment would be cobalt here, beta decay into this counter. Now, if the experiments were just like that, you don't have to do it because the two are the same. It's the same experiment. Cobalt here, counter here, cobalt here, counter here. To make the two not the same, you have to do something like this. Put a coil around here. The coil carries a current. Then the mirror image experiment would have a coil carrying a current this way. So you see that now these two experiments are not exactly the same. And they are exact mirror images of each other, but they are not the same. And therefore, if you test whether these two give the same result, you are testing whether mirror image is whether an experiment and this mirror image are the same. So you are testing right-left symmetry. That is to say, you are testing right parity conservation. When we proposed this in 1956, together with some 4 or 5 other experiments, they all looked difficult. And furthermore, nobody believed that if he does this experiment, it would not show parity conservation. So people had a tendency to say, so what? It's a difficult experiment. After I do it, it would not give any great excitement. So people were not willing to do it, with one exception, and that is Wu Jianxiong. Wu Jianxiong was a great expert on beta decay. She was already the leading experimental physicist in beta decay. And she had the insight. She believed that, yes, this experiment is difficult. Yes, after I do it, it's likely to prove parity conservation, so it's not a big deal. But I want to do it because a fundamental experiment about a fundamental law of nature should be tested and should not be just believed without the experimental proof. That was her greatness. So she went to do this experiment. And this is her equipment. In those days, it was considered a large piece of equipment. This big thing here is the magnet. The magnet is really the coil that is the coil that I showed in the previous diagram is the symbol of this magnet. This piece of equipment is now in the Smithsonian Museum in Washington, D.C. But with this piece of equipment, after 6 months of struggle, 6 months of struggle for doing one experiment in those days was considered a long and difficult experiment. And after 6 months of struggle, she found that the right and left, the two experiments were not the same. And that caused a great excitement because a fundamental law of nature has been overthrown. And rapidly, people began to say that if that is the case, the other parity tests that Lee and I proposed in our 1956 paper should also be tried. So they went on to try it. And one group, Lederman and Garvin, did an experiment with an accelerator. Wu's experiment did not need an accelerator because the cobalt nucleus was manufactured in reactors, and she didn't need an accelerator herself. But Lederman and Garvin went to do an experiment in an accelerator, and in 48 hours they did a beautiful experiment of a different type. It's a pi mu e decay, which very clearly also showed parity non-conservation. I remembered I was giving a talk in Princeton after the Lederman-Garvin experiment was finished. So I told the students that there was the Wu experiment, which took half a year, and after that, when Lederman-Garvin learned about this exciting result, they went to do a different experiment, also testing parity conservation. And in 48 hours, they found parity non-conservation in another phenomenon. So a student said, if that experiment takes only 48 hours, why was it not done in the previous 6 months? The answer is, if you don't know that you are going to have an exciting result, you don't spend a lot of effort thinking about it. Garvin and Lederman in fact had refused our suggestion half a year later to do that experiment. But they did not have the insight of Wu saying that that experiment should be done. So they didn't want to do it. But once it was known that this is something which is very exciting, they went on to do it, and in a very ingenious and beautiful experiment, they also showed parity non-conservation. So that caused a great excitement. And in the in the years 1957 and 1958, the whole of the physics community was interested in parity non-conservation because of it's a fundamental principle. It entangles the concept of symmetry, which everybody realizes at that time was one of the fundamental concepts in the structure of the physical universe. And also because one can do parity non-conservation not only in particle physics, but also in nuclear physics, in atomic physics. In other words, it's an across-the-board phenomenon. The great excitement caused by the violation of a basic symmetry focused attention on the role of symmetry in fundamental physics. Heisenberg and Pauli apparently believed that the groping in the fog days of the 1920s were back again. In the 1920s, as I had earlier told you, there was confusion, and people were doing physics not in a logical way, but in a groping way, because they knew that there were very important principles, but they didn't know where to find these principles, so they were groping. Heisenberg and Pauli had experienced that period of the 1920s, not my generation. My generation was not yet born, most of us at that time. But in the mid-1950s, Heisenberg and Pauli thought that that groping days were again. So they began to write down, to push for what was called a word equation. And there ensued a period of great excitement and great confusion. And many years later, just before Heisenberg died, he wrote an autobiography in which you read the sentence, "I had never seen Wolfgang," Wolfgang was Pauli, "I had never seen Wolfgang so excited as in 1957 to 1958. But their great excitement, their collaboration ended in failure, and in particular ended in a bitter scene in the summer of 1958 in Geneva, in which Heisenberg and Pauli quarreled at the international conference publicly, in which Pauli called Heisenberg absolutely stupid. We young physicists were very amazed at the strong language that Pauli used against Heisenberg. We are also impressed by the fact that Heisenberg took it very calmly. Heisenberg defended his ideas and did not use any strong words. It turned out that Pauli was already very sick. He didn't know it. Nobody knew it. He died within 2 months of that conference of cancer. What is our present situation of parity non-conservation? As it turned out, parity violation and later CP violation were explored in detail phenomenologically. So today we know how parity is not conserved in various interactions, in beta decay, in theta-tau decay, and in other decays. but no basic understanding of why such violations exist. Our present understanding of parity non-conservation is a phenomenological one. It does not touch any detailed principle. So this remains one of the puzzles of fundamental physics. The last symmetry subject I want to mention is gauge symmetry. Maxwell equations have Lorentz symmetry. I had earlier told you that after Maxwell wrote down his equations, it was half a century later that Einstein and Minkowski found that there's a symmetry, the Lorentz symmetry of Maxwell's equations. It turned out that Maxwell's equations have another symmetry. It's called gauge symmetry. This was discovered mainly by Hermann Weyl in the years 1918 and 1929. Hermann Weyl was one of the great the great mathematicians of the 20th century. At the beginning of the 20th century, the two leading mathematicians were Hilbert and Poincaré. And most mathematicians now would say that the successor to Hilbert and Poincaré was Hermann Weyl. But Hermann Weyl also liked to dabble in physics, mostly in a philosophical way. And the principle of gauge symmetry was a result of Hermann Weyl's excursion into the philosophy of physics. Weyl's motivation was to geometrize electromagnetism because before 1918, in 1915 and 1916, Einstein had geometrized gravity. You know that gravity, in terms of Einstein's ideas, is because of curved space-time. So Einstein insisted that the other fundamental interaction, which was known at that time, namely electromagnetism, should also be geometrized. And Hermann Weyl took up this challenge. And eventually found that Maxwell's equations and quantum mechanics were invariant under joint transformation. The joint transformation was, if you take, the second line is what already was known in the 19th century. You change a mu into a mu prime by adding to it a gradient. And the curl of a mu prime is the same as the curl of A. And that flexibility of the definition of the vector potential was known already since the beginning with Thomson. What Hermann Weyl found was that in quantum mechanics, if you change psi at the same time to psi prime by multiplying a phase factor onto psi, then these two together leave quantum mechanics invariant. And that is called gauge transformation. In fact, this is called the gauge transformation of the first kind. This is called gauge transformation of the second kind by Weyl. Throughout the 1930s and 1940s, gauge invariance was well known to theoretical physicists, but it produced nothing really new. People knew that there's this invariance. Its only use seemed to be for a young theorist to spring a small question at the end of a seminar. Is your result the gauge invariant? If you calculate a complicated thing, the final result has to be gauge invariant. And that is in fact a good thing with which you can test whether you have made any mistakes. If you start with the theory which is obviously gauge invariant, and you end up with a result which is not gauge invariant, that means you have made a mistake in the middle. And as far as the young people of the 1940s and 50s were concerned, this seems to be the only use in which gauge invariance was made of. Then in 1954, gauge symmetry was generalized. There were several motivations for this generalization. The first was searching for a principle for interaction. That's the first motivation. There were many new particles at that time. There were theta particles, there were tau particles, there were lambdas, there were xi's, and there was the question of how these particles interact with each other. And their spins and parities and charges were experimentally measured. So now you have this collection of new particles. How do they interact with each other? And that was what people were doing. So there were books written about scalar mesons with scalar interaction, scalar mesons with vector interaction, and so on and so forth. The question that Mills and I asked, one question that Mills and I asked, is that this is not going to be fundamental enough. There must be a principle of interaction. The second motivation is that the charge, this was in our paper of 1954, the electric charge serves as a source of electromagnetic field. An important concept in this case is gauge invariance. Gauge invariance relates electron conservation of charge with the gauge transformation, and that gives rise to the Maxwell equations. We have tried to generalize this concept of gauge invariance to apply to other symmetry law, conservation laws. What we applied it to was the isotopic conservation. Isotopic spin was found to be an experimental conservation law. So we are asking, here is a conservation law somewhat similar to conservation charge. Should it also generate a interaction? We also had a third motivation, and this was also in our paper. We said it is pointed out that the usual principle of invariance under isotopic spin rotation is not consistent with the concept of localized fields. At that time, there was already local fields. That's Maxwell's equations. Local fields means that everything is just defined independently at different points. They influence each other, but nevertheless, they are defined at different points. We pointed out that the gauge transformation of Hermann-Weyl was usually thought of with that alpha as a constant independent of space-time. And that concept is not in the spirit of field theory. So anyway, with all three of these motivations, we converge on one generalization of Maxwell's equations. And that goes as follows. First, in ordinary electromagnetism, we have this quantity in quantum mechanics. And if you now make a transformation of x equal to this, you change psi into psi prime, like what I showed you in a previous transparency. I substitute that in here, then this x becomes this. Now, this differential operator operating on the product gives two terms. So this becomes now this. You recognize that when this differential operates on this psi prime, you get this term. When the differential operates on this, you get this term. Comma mu means d dx mu. And this term goes back here. Which, of course, I can write in this fashion if I identify this with this. In other words, I identify this. So that is what was done by Hermann-Weyl. This is gauge transformation of first kind, gauge transformation of the second kind. And after that transformation, you find that the X looks just, it's in form invariant. So what the Mills and I did was to say that, okay, we generalize this. If you have isotopic spin in your system, then the psi is not just a one component, it's a two component one. So psi is thought of as a column matrix with two entries, one for proton, the other for neutron. And so instead of the A, we have the B here, and the B has to be a 2 by 2 matrix. So we propose that B is a 2 by 2 Hermitian matrix. And copying from previous transparency, we write psi equal to S times psi prime, where S is a 2 by 2 matrix. And it has to be a 2 by 2 unitary matrix to conserve probability. So I substitute that psi into the X, I get this. And just like in the previous transparency, you do this calculation, and the alpha comma mu becomes this term. And so that is equal to this, and you identify this, the sum of these two with this, so you get this equation. So very rapidly, within a few minutes, you arrive at the generalized gauge transformation of the first kind and the generalized gauge transformation of the second kind. In fact, I did that already when I was a graduate student in Chicago. Because when I was a graduate student in Chicago, there were already new particles, and there was the question of how they interact, so I tried this. Then the next step is, of course, I copied Maxwell. Maxwell had the curl of A becomes the field. So I wrote F mu nu equal to, except now everything is a 2 by 2 matrix. And then I can calculate F prime is equal to B mu comma nu prime minus B prime nu comma mu. And then, of course, I can substitute the previous B prime into it and begin to calculate. And became a lengthy calculation, and the more I calculate, the more it became complicated. And it's an ugly structure. So I have to give up. If you have a good idea, my advice is struggle with it for a couple of days. If you don't get anywhere, you have to let it go. So I let go of the idea. But after half a year or maybe 8 months, I decided this is a very good idea, so I do it again and got stuck at the same point. And this repeated several times until 1954 when I was at Brookhaven. And Bob Mills was a postdoc, and he shared my office. So we began to discuss many problems in physics. And one day I mentioned that this is a very good idea, but after this equation, everything became very ugly and didn't go anywhere. It was then that we hit upon the idea, maybe we should change this equation. Maybe this is just not just a curve. Maybe we can do something else. And the something else was, we said, okay, let's add some quadratic terms. If it still doesn't work, we'll add cubic terms. Fortunately, after we tried this quadratic term, in fact, within 1 day, we find that that is the right thing. If you take this to be the definition of F mu nu, rather than the simple one without the quadratic term, then the result is very simple. It becomes, this F prime becomes equal to this, which is a very beautiful thing. So we found this quadratic term by requiring that the transformation of F looks simple. Later on, we realized that from the mathematician's viewpoint, it was the quadratic term is necessary. But that's not known to us in 1954. So we wrote this, and this became the non-abelian gauge theory. What we did at that time was psi was a column matrix of 2 elements. B was a 2 by 2 matrix. But it turns out that this can be generalized. Generalization to more complicated groups than SU2 is immediate. Isotopic spin invariance is a 2 by 2 is a SU2 invariance. But if you go to more complicated groups, everything follows exactly the same. Only you make things larger representations. For example, you can make SU3 or in fact any Lie groups. After that, after you realized that it can be generalized to any groups, it is better, instead of writing as matrices, rewrite it into component form. And here is the non-abelian gauge theory in component form. Maxwell's equation is like this. I'm sure you realize this. This equation is a combination of Faraday's law and Gauss' law. This equation this is the source, is the combination of Coulomb's law and Ampere's law. I'm sure you have seen these 2 equations. With the non-abelian gauge theory, you have these equations. First, there is an additional index I. There's an additional index I because when the group becomes larger than electromagnetic group, there are more components. With SU2, there are 3 components. With SU3, there are 8 components. So this I designates the component. If it is a U1, the electromagnetism, I is always equal to 1, so you can drop it and it becomes this equation. So this has more components. And here you have quadratic equations because of that commutator that I had shown before. And what are these Cijks? Cijk is the so-called structure constant. It characterizes as a group, and the Cijk satisfies this algebraic equation. This equation is sometimes called Jacobi equation. Now what happened was, I had told you earlier that group theory gradually became very important in the 19th century. In the latter part of the 19th century, Sophus Lie generalized group theory into continuous groups. He was talking about the groups of transformations, but now we know that the idea of the group is much more general than groups of transformations, and there's a symbolic way of doing it. But the immediate question was, what are the different types of Lie groups? And that the one who contributed most to that was Cartan. Cartan, in his thesis, studied, before Cartan, there was the concept of structure constant was already known. This was before Cartan. And this equation was known. This equation determines the structure of a Lie group. It's called, the study of this is called Lie algebra, because this is an algebraic equation. And the study of Lie algebra and the study of Lie group are deeply related. This was already known before Cartan. But Cartan's great contribution was that he solved this equation. He showed in 1895 that this set of equations has 5 different types of solutions 4 different types of solutions, plus 5 exceptional type of solutions. So that was the great contribution, which at one stroke clarified the structure, in some sense, of all Lie groups. And all this SU2, SU3, G2 are different types of solutions of this Lie algebra. About the origin of non-abelian gauge theory, I want to make a few historical comments. First, I had said that when Weyl wrote down in 1918 and 1919 his electromagnetic gauge theory, Einstein objected to it. And Pauli was also objected to Weyl's idea. Pauli was a young man. He was born in the year 1900. So he was a very young man, but he was already very famous. And he also objected to Weyl's 1918 and 1919 paper. But his objection was not like the one that I told you about Einstein's, about going around the loop and not being able to standardize rulers and clocks, but on philosophical grounds. But according to Mera and Rechberg, and according to Henry, these are very distinguished historians of science, Pauli's objections to Weyl were later of importance to the emphasis in the 1920s of using only observables in theory. You know, only using observables in theory was a very important idea, which was one of the guides that led to Heisenberg's invention of quantum mechanics. Apparently, Pauli's objection to Weyl had something to do with the idea of observables. This is a subject which I think is worth looking into in more detail for history of physics. Another remark was Weyl was, until his death, devoted to the idea of gauge invariance. He explicitly stated 6 months before his death in 1955 that the strongest argument for gauge theory was its relationship to charge conservation. He was an old man, and just a few months before his death, he was still very much interested in gauge theory, and he did not know that Mears and I had in fact generalized this idea to non-abelian Lie groups. In the 1980s, in an article that I wrote about Hermann Weyl, I had the following passage. This was written in 1985. I had met Weyl in 1949 when I went to the Institute for Advanced Study in Princeton as a young member. I saw him from time to time in the next years, 1949 to 1955. He was approachable, but I don't remember having discussed physics or mathematics with him at any time. It was mostly at cocktail parties that I saw Hermann Weyl. His continued interest in the idea of gauge fields was not known among the physicists. Neither Oppenheimer nor Pauli ever mentioned it. I suspect they also did not tell Weyl of the 1954 papers of Mears and mine. Had they done that, or had Weyl somehow crossed our paper, I imagine he would have been pleased and excited, for we had put together two things that were very close to his heart: gauge invariance and non-abelian Lie groups. He was close to non-abelian Lie groups because perhaps his greatest contribution to 20th century physics was his papers of 1925, when he built on Cartan's theory and developed the representation theory of Lie groups. I had mentioned the last time that, for example, SO3, three-dimensional rotation group, has representations of different sizes. So every Lie group should also have representations. But how to find these representations, how to characterize these representations, these were the great contribution of Hermann Weyl of 1925. So Lie groups was one of his dear objects. And as was evident from what I just quoted about what he said 6 months before he died, that the gauge invariance was another of his favorite babies. Non-abelian gauge theory was considered a beautiful and unique generalization of Maxwell's equations already in the 1950s. But it had too much symmetry and was not in agreement with experiments until the idea of symmetry breaking. The idea of symmetry breaking did not originate with trying to fit experiments into non-abelian gauge theory. Symmetry breaking came from other ideas. What it really means, symmetry breaking means that you have equations which algebraically is totally symmetrical. But the experimental manifestation of those field theory, those mathematically symmetrical field theory, may not be symmetrical. This is a subtle idea which gradually came into field theory in the 1960s. And in 1967, Steve Weinberg boldly proposed that non-abelian gauge theory is correct, and the too much symmetry question could be resolved by the idea of broken symmetry. And that led to what is now called the standard model, which is a symmetry breaking version of non-abelian gauge theory for weak interactions and strong interactions. The reason that the gauge theory is good, non-abelian gauge theory is good, is because the symmetry is good for renormalization. This is an important statement. You know that the renormalization was born because in the 1930s, after people did a lot of field theory, they found that there was beautiful agreement with experiment. But if you do higher order calculations, it diverges. That's called the divergence difficulty. That was the prevalent big problem when I was the beginning graduate student in Chicago. How was that cured? It was cured by the renormalization program. If you look at the renormalization program, for example, you probably have learned about Feynman diagrams. The reason that the Feynman diagrams was able to contain the divergence problem was because Feynman used Lorentz symmetry to the maximum. You all have used the notation P slash. That was an idea invented by Feynman. In the 1930s, people didn't do that. So the Lorentz symmetry was known to be in the theory, but in the calculations, people did not utilize that to the full. And it was Feynman who utilized the symmetry to the full by introducing such notations as P slash. And once you got accustomed to that, you know that a maximum use of symmetry guides you toward the renormalization program. And now we know that the gauge theory, non-abelian gauge theory, is renormalizable. The reason is because its algebraic structure is very symmetrical, and that was the great contribution of 't Hooft of 1971 or 72. So by the late 70s, it became clear that fundamental interactions, strong and weak, are governed by gauge principles, which of course are based on symmetry. So I coined the phrase, symmetry dictates interaction. And that is generally accepted as a fundamental direction in which in which interactions in nature are structured. So I had shown this influence of symmetry in physics on the left side in an earlier transparency. Now we have to generalize that, because there is a new branch called gauge symmetry, and there's a new principle called gauge symmetry dictates interaction. And out of that, we understand strong force, electromagnetic force, and weak force. How about gravity? But gravity and quantum mechanics have not been successfully amalgamated. I had said that the symmetry is good for renormalization. Gravity is very, very symmetrical. In fact, I think I had shown you a transparency showing you what Einstein said in his old age about general relativity. He said that special relativity's symmetry is not enough. So he tried to generalize that. And that was, in fact, the largest symmetry that you can imagine. But the largest symmetry, namely the symmetry of general relativity, somehow has not been found to give renormalization. So in some sense, that is this slide says the defect that we still have today of our understanding of fundamental interactions, because gravity has not been brought into the fold. Why? Nobody knows at this moment. I want to mention that there is deep meaning of gauge theory in mathematics. This was not known to Mears and I for many years. In the late 1960s, I was teaching a course in general relativity. And so one day I wrote down on the blackboard this equation, which I'm sure if you have learned the general relativity or Riemannian geometry, you have seen this formula for the Riemann curvature tensor. As I wrote this on the blackboard, it occurred to me that this looks very much like this equation, which I was very familiar with, because after all, this part is a curve, and this part is quadratic, just like this. So I remember that after I went to my office after the lecture, I wrote these two down on a pad and made comparison. And then I realized, in fact, they are exactly the same if you identify the B with the proper notation here. With the proper notation, the two equations are not similar. They are exactly the same. So I went to see my colleague, Jim Simons, who was department chairman, who was a distinguished mathematician. You might have heard of him. He is now a billionaire because in the 1970s, he abandoned mathematics and went into the Wall Street. And he is now the most successful hedge fund manager in Wall Street. And he is going to manage a 100 billion US dollar fund, which would be the largest hedge fund in the world. That single fund would be 10% of all the hedge funds put together in the world. He was a very exuberant person with all kinds of ideas. At that time, he had nothing to do with Wall Street. He was a pure mathematician. So I went to him and told him about the similarity of these equations. He said, they must both be fiber bundles. So I said, what is a fiber bundle? And he gave me a book. The book was impossible to read because modern mathematics is too abstract. There's no meat in it. It's all bones, and I couldn't understand that. But later on, I asked him to give us a series of lectures about fiber bundles. And I greatly benefited from a simple understanding of fiber bundles. And I know one of the great personalities in that theory is Professor S.S. Chen, who in fact was a professor in Xinlianda when I was a student, and I had taken a course of differential geometry from Professor Chen. Professor Chen died 2 years ago at the age of 93. I had later written in the 1980s the following passage about a conversation between Chen and me. In 1975, impressed with the fact that gauge theories are connections on fiber bundles, I drove to the house of Chen in El Cerrito near Berkeley. I'd taken courses with him in the early 1940s when he was a young professor and I an undergraduate student at the National Southwest Associated University in Kunming, China. That was before fiber bundles had become important in differential geometry and before Chen had made history with his contributions to the generalized Gauss-Bonnet theorem and the Chen class. We had much to talk about: friends, relatives, China. When our conversation turned to fiber bundles, I told him that I had finally learned from Jim Simons the beauty of fiber bundle theory and the profound Chen-Weir theorem. Weir was a great mathematician. Some people regarded Weir as the greatest mathematician in the latter part of the 20th century. In other words, they would say the greatest mathematicians of the 20th century were to start with Hilbert and Poincaré, and then Hermann Weyl, then André Weir. I said I found it amazing that gauge theories are exactly connections on fiber bundles, which the mathematicians developed without reference to the physical world. That's what I said. I added, this is both thrilling and puzzling, since you mathematicians dreamed up these concepts out of nowhere. He immediately protested, no, these concepts were not dreamed up. They were natural and real. This was his own words, and it was true. From the mathematician's viewpoint, just building on the concept of beautiful structures, they have created the concept of fiber bundles. So then a fundamental question, how come these ideas, which were natural and real to a mathematician, without reference to the real world, why were they used in the real world? That is a puzzle about which there have been many discussions, but it's clear nobody will be able to answer it, to understand it. So we have seen that the concept of the vector potential has had a very complicated, very important history. So a few months ago, I published a paper about the evolution of the concept of the vector potential A, from a somewhat annoying flexibility in the definition of, in its definition, to an essential freedom of choice that determines fundamental forces. This was published with a colleague, Wu Qidai, in the International Journal of Modern Physics just a few months ago. I will outline to you approximately what we said. A was first used by Kelvin, Lord Kelvin, in 1851, who did recognize its non-uniqueness. He defined A as a vector whose curl is equal to the magnetic field. And he knew that it was not equal, not unique. You can add a gradient to it. In 3 papers, 1855 to 1865, Maxwell wrote down the Maxwell equations. The interesting thing is that these equations all contain A. In fact, if you look at those equations, you'll see that Maxwell got to the Maxwell's equations through A. So A was inherent in his thinking. And throughout his life, Maxwell's wrote down equations always with the A in it. Later on, Heaviside and Hertz, who came after Maxwell, in around 1885, independently found that the A could be eliminated. So that is the Heaviside Hertz form. I'm sure these are the forms that you have learned. These are the forms which are indeed simpler than the equations that Maxwell wrote down with A. And it is these equations that graduate students in the 20th century were taught. And when I learned in my sophomore year to my graduate student days, Maxwell's equations, they were always written in this form. It has several advantages. First, it looks simpler. Second, it exhibits a certain near symmetry between E and H, which was also observed by Heaviside and Hertz. In fact, Heaviside in 1892 after he had discovered this new form of Maxwell's equations, the duplex method, referring to his recasting of the Faraday's law as curl of E in parallel to the curl of B for the Ampere's law as Maxwell's has, eminently suited for displaying Maxwell's theory, and brings to light many useful relations which were formerly hidden from view by the intervention of the vector potential and its parasites. What he called parasite was the scalar potential. In other words, by eliminating the 4 components of A, Heaviside got those equations which he felt was much simpler. So he called vector potential, he called A vector potential and its parasite. In another occasion, Heaviside wrote, in the present method we are, from the first and last, in contact with those quantities which are believed to have physical significance, instead of with the mathematical functions of an essentially indeterminate nature, indeterminate because of the possibility of gauge transformation, and with the laws connecting them in simplest form. But today we know that you can write down Maxwell's equation with A, but the concept of A cannot be eliminated because the Aharonov-Bohm effect shows that A cannot be completely eliminated. It has a physical significance. And the flexibility of its definition, the flexibility in the definition of A, is precisely the symmetry that determines the structure of the electromagnetic field. And in fact, it is it is precisely that symmetry that determines the structure of all gauge fields. This last slide is really the spirit of gauge theory. I had earlier mentioned that there is some mysterious relationship between math and physics. In fact, in 1961, Marshall Stone, who at that time was the department chairman of mathematics of Chicago University had a great reputation in mathematics and physics immediately after the Second World War. It had a great reputation in physics because they succeeded in attracting Enrico Fermi to become a professor there. And that's why I went to the University of Chicago. It became great in mathematics because Marshall Stone became its mathematics chairman. And under his guidance, they acquired André Weil, the one that I mentioned before. They acquired Chen Shenshen. And so in the 50s and the early 60s, Chicago University's mathematics department was very famous. In 1961, Marshall Stone wrote an article which had the following paragraph. The discovery that mathematics is independent of the physical world was his main point. He said mathematics are now seen to have no necessary connections with the physical world beyond the vague and mystifying one implicit in the statement that thinking takes place in the brain. Why did Marshall Stone say this? Because in the first half of the 20th century, mathematics became axiomatized. There was a tendency this was under Hilbert's influence, and they want to make mathematics a purely logical structure. So, and that was very successful. So when you read Feiberbander's book, it was a mathematical structure. It's in the style of axioms. And so Marshall Stone in 1961 said, the great contribution of early 20th century mathematics was to break away from reality. In the 19th century, in the early centuries, physics and mathematics were deeply related. But Stone thought that that is ended. And indeed, Freeman Dyson, a great physicist, the one who really understood the renormalization theory in total, and a colleague of mine for many years, he wrote in a bulletin of the Mathematical Society in 1972. He said, as a working physicist, I'm acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce. Discussing this divorce, the physicist Ray Yost remarked the other day, as usual in such affairs, one of the two parties has clearly got the worst of it. What the Ray Yost meant here was that the divorce was bad for physics, and it was true. But mathematics and physics remarried since the 1970s, thanks to gauge theory and string theory. So now there are many people who are working in between mathematics and physics. That remarriage had a lot to do with this table. This table was published by T.D. Wu and I in the mid-1970s. I had earlier said to you that I had invited Jim Simons to explain to us at Stony Brook, physicists at Stony Brook, the gist of fiber bundle theory. And after we heard many of his lectures, Wu and I understood the gist of the mathematics of fiber bundles. So we made this dictionary in one of our papers. On the left side of this paper is the gauge field terminology. On the right is fiber bundle terminology. They were exactly the same. What we call a gauge, they called the principal coordinate bundle. What we called, for example, phase factor, they called it parallel displacement. The field strengths become curvature. Electromagnetism is connections of a U1 bundle. Dirac's monopole quantization becomes classification of a U1 bundle according to the first Chern class, etc., etc. These correspondences were exact. And after we understood what Jim Simons taught us, we found this table to be very useful. But when we came to this source is the divergence of F mu nu. It consists of the current and the charge density. We asked Jim Simons, what is this? He said, we don't deal with this quantity. So that's why in our publication there's a question mark. That's very fortunate. Because I showed this article to Singer. Singer is a distinguished mathematician, chair professor at the MIT when he was visiting Stony Brook. In fact, he and I were contemporaries as graduate students in Chicago. He started out being also a physics graduate student, but in the midst of his career, he switched to mathematics. So he got a mathematics PhD in Chicago and later became a professor at MIT. And when I showed him this, he got intensely interested. Because although the mathematicians in one style is doing very abstract mathematics, they of course are pleased that their abstract mathematics has something to do with physics, with reality. So he took our paper and he showed this to Atiyah. Atiyah is one of the great contemporary mathematicians in Cambridge, at that time in Cambridge, England. And the two of them realized that this is in fact an extremely interesting quantity. And so this question mark has something to do with getting the mathematicians interested in physics again. And that was the beginning of the remarriage of mathematics and physics. I had reflected on the true relationship between mathematics and physics and have a two-leaves theory exhibited here. Mathematics and physics are like two leaves. They mostly do not overlap, but in a few percent of each domain, there is an overlap. And the amazing thing is that in that overlap region, ideas and concepts are shared in a very exact way. However, deep as the relationship is between mathematics and physics, it would be wrong, however, to think that the two disciplines overlap that much. They do not. They have their separate aims and tastes. They have distinctly different value judgments, and they have different traditions. At the fundamental conceptual level, they amazingly share some concepts, but even there, the life force of each discipline runs along its own veins. In other words, the direction of development of each is not dictated by what happens in the other discipline. It has its own tradition. I have talked for many hours now with you about the three melodies that appear again and again in 20th century theoretical physics. Quantization, phase factor, and symmetry. How about the future melodies? Maxwell wrote a 2-volume treatise which was a summary of his 3 great papers. In the preface to the treatise, he wrote, "As I proceeded with the study of Faraday, I perceived that his method of conceiving the phenomena was also a mathematical one, though not exhibited in the conventional form of mathematical symbols. When I had translated what I considered to be Faraday's idea into a mathematical form, I found that in general the results of the two methods coincided, so that the same phenomena were accounted for, and the same laws of action deduced by both methods, but that Faraday's methods resemble those in which we begin with the whole and arrive at the parts by analysis, while in the ordinary mathematical method were founded on the principle of beginning with the parts and building up the whole by synthesis. I believe this passage is extremely important because that showed how Maxwell got onto Maxwell's equations. What he really is saying here, what he called the whole, was this equation, that if you integrate around a loop, you get the total current inside. This was Faraday's idea. This idea written as a differential equation is this. Today, of course, if we integrate this, we make a double integral of this and use Stokes' theorem. I go from here to here. And what Maxwell is saying was that when he read Faraday was no mathematician, no equations. If you read the thousands of pages of Faraday, there's not a single equation. But he described in words this equation. And Maxwell's genius was he understood what Faraday said and used the Stokes equation and wrote it into this form. The Stokes theorem was very important, and today in differential geometry they wrote this in this very, very condensed and potent form. When Faraday died on August 25, 1867, Maxwell published a tribute to him in Nature. Maxwell wrote, "The way in which Faraday made use of the idea of lines of force in coordinating the phenomena of magneto-electric induction shows him to have been in reality a mathematician of a very high order, one from whom the mathematicians of the future may derive valuable and fertile methods. From the straight lines of Euclid to the lines of force of Faraday, this has been the character of the ideas by which science has been advanced. And by the free use of dynamical as well as geometrical ideas, we may hope for future advance." If you ask me where the next melody for theoretical physics is going to come from, I would say it would come from probably some deep mathematical concept which might originate not from a professional mathematician, but from a physicist. Thank you. I'll be very happy to discuss any questions with you if you have any. You may have heard that I didn't go into this. I had said that with fiber bundles, mathematics and physics are remarried. And especially in the last 20 or 30 years, there is a new branch of theoretical physics called string theory. And string theory is highly mathematical. So there are many papers published in the last 20 or 30 years on string theory. I know nothing about string theory. It is a highly abstract type of consideration which would take me months before I can even find the beginning ideas in it. But it clearly has intellectual challenge because in the last 20 or 30 years, I would say the brightest 20% of theoretical graduate students all over the world have all gone into that field. A field without without intellectual challenge would not be able to have so many bright young people getting into it. And furthermore, string theory has produced results in mathematics which the mathematicians are very, very much interested in. Atiyah, the one that I mentioned a few minutes ago, in publishing his collected works, devoted a whole volume to the relationship between mathematics and physics, and much of it has deep connections to what has come out of string theory. However, string theory has not made any contact with reality. And recently, there are there have appeared two books criticizing in very severe terms string theory. I should mention these two books to you. One is written by a young man named Voigt, W-O-I-T, and the book is called Not Even Wrong. Not Even Wrong was a famous joke by Pauli. I had mentioned Pauli several times. I knew Pauli well. He was 22 years my senior and a towering figure when I was a young physicist. And he liked to make very sarcastic statements. And one story was, there were many stories about Pauli. One story was one day a young physicist wrote a long paper and gave it to Pauli and said, Professor Pauli, could you read my paper and comment on it? So Pauli took the paper. And a few days later, the man saw Pauli again and asked, Professor Pauli, would you like to tell me what your opinion is? Pauli looked at me and said, it is not even wrong. So not even wrong became a kind of a statement that you apply to something which is worse than wrong, of course. And Voigt's book is entitled Not Even Wrong. Another is written by a physicist named Smolin, S-M-O-L-I-N. And it's called, I think it's called The Trouble with Physics. But both books are strong attacks on string theory. So I think you would probably find both books very interesting. Probably the university library has these books.
the very first of the lecture, you have mentioned beta decay experiments actually didn't prove that the wavelet symmetry. But in the last, you have quoted that symmetry dictates interactions. So could you tell us more whether symmetry or the parity actually dominates interactions of particles?
I'm not. You are asking me. I had said that early beta decay experiments did not prove or disprove parity conservation. It was a wrong belief that it proved parity conservation. And you ask me, what do I say now? Is that what happened is that all weak interactions do not observe right-left symmetry. And how it does not observe right-left symmetry, we have, through the last 40 years of experiments, understood or described. But why, we don't understand. So if you now say, okay, I am going to do an experiment on the beta decay of nucleus XXX, is it going to observe parity conservation? I would tell you, no, it would not observe. And I will tell you how much it violates parity. But I don't know, I have a formula which I can grind out that asymmetry. But why it is so, I do not know. There's no fundamental reason that anybody has really invented to tell why nature is not absolutely right-left symmetrical. So we call that, we have a phenomenological understanding, but no basic understanding. I think I'll take this opportunity to say something. If you review what has happened in the 20th century, there are great new principles which have been discovered by people. And this is perhaps unique in the history of physics. If you ask me, what is the situation today? I would say the 21st century is very unlikely to produce the same great fundamental discoveries of the 20th century. But that does not mean that physics is not worth studying. It is only that the emphasis of physics in the 21st century will be very different. And it is both good for you and bad for you. It's bad for you because if you want to create something which rivals quantum mechanics or rivals special relativity, I would say it's very unlikely you will succeed. But it's good for you because now quantum mechanics, relativity, and all the things that come out of it has now opened so many doors. You can now have many, many things. Take material sciences. Material sciences is a huge field with extremely interesting things. None of them would rank as something like quantum mechanics, but all of them are very interested in physics, and furthermore, they are extremely useful, and they would be of great benefit if you make any discoveries in it to mankind, and you may become a billionaire just because you go into that. And that the examples of that is everywhere to be found. There's physics is now used in medicine, in computers, in the internet, And many, many billionaires have been created in the last 20 years by internet. And all of that are consequences of the fundamental discoveries of 20th and 19th century physics. It's only different types of things that will prosper in the 21st century compared with the 20th century. Okay, if no further questions, good luck.